All right. Hello, everyone, and welcome to Handmade Hero, the show where we code an entire game from scratch, live on Twitch, no libraries, no engines, so we can see absolutely everything that has to go on to make a game actually work. And there's a fantastic amount of stuff in there that has to go on to make a game work. And it can be really fascinating to kind of get in there and see all the stuff that happens, I think, anyway. It's really interesting to me, and I hope it's interesting to you as well. We are on day 50 right now, and we are just about to finish up the sort of collision detection stuff that we were doing. Basically, what we're in the middle of right now is a pass over the code at the beginning where we're basically speccing out everything that we want in our engine. So we're doing basically crappy versions of all of the things that we think we will need to make the game run properly so that we have some functional skeleton in place that we can look at and go, okay, we see how everything works together. We see what the requirements basically are for each thing. Now when we go do industrial strength versions of each of these pieces of code, first of all, we have the other pieces of code in place working, if albeit jankily, which is kind of important. So we can see how things work together as we make new components. But also, it's so that when we go off and make a new component, and we're trying to do like a good high quality version of it, we're not doing that in a vacuum, because when you do stuff like that in a vacuum, you tend to make a lot of mistakes in terms of how it will interface with other things, and you forget certain requirements that maybe you wouldn't have thought of if you hadn't have looked at the usage code first. So always write the usage code first, big mantra of mine, and that is exactly what we're doing. We've gotten to the point where we have a collision detector that basically actually already works. It works better than I thought it was going to work. I thought this version was going to be jankier than it was, but it's not at the moment. But that's okay, because we still have a feature to add to it anyway, so I'm going to do a little bit more on the collision detector before we put it to bed and say, okay, everything else that's going to happen with collision detection is going to happen when we do the final version of it. But there is one more thing that I want to do, because I think it's relatively important to have something like it in place, and that is basically area-based collision detection. So we'll talk about that in a second. For now, if you are one of the fine fellows who has pre-ordered Handmade Hero from handmadehero.org, you will note that today we are on day 50, which means that if you download the source code that comes with the game from last night's post, day 49 source code is in there. Unzip day 49 zip into a directory, and you'll be right where I am today. So if you want to follow along, that is the day to use. Okay, let's get started here. Let's take a look at where we were. So we did some debugging yesterday. Our collision detector is now, unfortunately, more solid than I would have wanted it to be. So we basically have two things to do today. One is that we have to actually do gliding now, like we want to be able to glide along edges instead of stop. And the other is I would like to have area-based collision detection. You'll notice that it's just point-based collision detection right now. It's that point at the base of his feet, so he can kind of go into objects slightly, which we don't want either. So we're basically just going to fix those two things today. That's our primary goal. The first one is probably a little harder than the second one in terms conceptually, because I already talked about the math behind the skating, so you kind of already know what we're going to do there. And so right now, all we really need to talk about is how we're going to do that area-based stuff. And so I guess what I'll do is I'll start off with that, because in case that takes the whole time, we can always do skating on Monday. And the skating is, like I said, we already talked about the math, so it's not going to be as big of an investment. So let's talk about what's going on here over on the whiteboard, or as we might call it, the tan board. So I guess it kind of looks like a chalkboard now. So what we were doing, right, the way we implemented our collision detector is we wanted to start doing collision detection where we knew when we would hit a wall, instead of just taking a point that we were at and a point that we were trying to go to over one time step, right? This is one time step, one frame, and saying, is this inside something or not, right? And when we did that, that was problematic because it meant that we couldn't do skating like we would want to do, and there's a bunch of other problems that we were going to have with that, like tunneling. There were problems with doing it this way. So what we decided to do was switch to a method where we actually solve for the time at which we would hit something. So we solve for that intersection point. So now we know between the 2 points, we actually check if any collision could have happened along there, right? But in order to do that, we made a simplifying assumption, which is we simplify it down to checking a line versus whatever the shape is that we were collision detecting against. In this case, we were collision detecting against 4 walls of a tile. And in that simplification down to a line, obviously that means that the person, that little fellow in there, he doesn't have any area at all. He's just a point, right? He's a point moving along a line. That's all we're testing. So what we need to do is now talk about how to make him a little bigger. And I'm going to use the simplification that we're just going to make him rectangular, because that's going to make it easier for us to implement, because we're not doing the final collision detection now. But what I'm going to talk about is actually going to be the same. The actual theory behind it is the same no matter what shape he is. And so I'm going to talk about him as if he was a circle as well, and stuff like that, just so that you understand that conceptually the way that we're thinking about this actually doesn't matter, but implementation-wise, you have to step up to slightly stronger algorithms if you want to use dissimilar shapes. And I'll explain why in a second. So what we're doing here is we're going to talk about something called the Minkowski sum, also the Minkowski difference. And what's interesting about this is that, like, Minkowski algebra, there's like, Minkowski was probably a pretty cool dude. I don't really know anything about him, but I suspect that he actually has a lot to say about a lot of things. And unfortunately, I am one of those people who only learned enough about what he did to do collision detection. So really, it's one of those things that's like on the bucket list. I would love to go read all and actually really understand all of his algebra stuff and how he worked with shapes and everything, because I suspect that there's probably some really cool stuff that I could do if I understood it, and I don't. I never learned enough of it to really know. So I'm going to tell you what is basically the game version of Minkowski sum and difference, which is the stuff we need to know about the work he did. Oh, I'm losing my voice. This is going to be a gravelly one. Which is the stuff we need to know about what he did to basically do what we need to do for collision detection. Okay. So essentially what you could think about is, imagine I had two walls with a gap between them, okay? And these walls each have, let's say, if we took their center, I guess it's hard to call it necessarily a radius because it's not a circle, but imagine there's like a radius, which basically says, you know, how, the dimension here, right? They have a dimension of something, and we'll call that, I don't know, S for now, okay? So basically these walls have a dimension of S. So they are 2S this way and 2S this way. They're squares, let's say, okay? And then I've got my guy, right? And I've got my guy here, and he, let's say, has a radius of r. So he's 2r this way, 2r that way. And when I do my collision detection, what I want to do is I want to drive him through here, right? And we can see just intuitively that he's too large to fit. So there's no way that you're going to fit this. This opening is less than 2r, right? So there's no way he should be able to fit through here. But obviously, if we were doing collision detection the way I talked about doing it in the simpler form when I was teaching how to do that basic line intersection, well, if he shrinks down to a point, he'd fit through there no problem. We can easily pass rays through there. There's tons of rays that would pass straight on through there and not have a problem. So the question is, what can we do that would make it so that we could still do collision detection continuously along a ray like that, along a line, so that we actually get analytic and we know we don't tunnel through anything? What would we do to do that so that we could still solve it with a guy who had an actual size to him and not just a point? And so the interesting answer from Minkowski is that you can actually do a form of algebra on shapes. So in much the same way that you might imagine having something like a plus b equals c, right? An equation like you would learn in high school algebra or even earlier. You could imagine saying, oh, well, if I want to talk just about A, I can move the B to the other side and say it's A equals C minus B, right? And these are two ways of writing the same thing. That's really handy, right? Because this allows us, even just those basic operations allow us to do a lot of things. We've already used that a ton of times in all the code that we've written just so far in the game, and we'll use it a ton more. Algebra is just really handy. Those simple operations of being able to move things to either side and talk about what a particular variable equals. If you have some kind of hairy equation over here, it's pretty cool, right? And it's very powerful. Well, we can actually do stuff like that with shapes as well. What we can do, if we essentially think of this as being a point, right, that has this radius here, and that radius is what gives it its volume. instead of thinking this as a having to cast, right, like what we would do if we wanted to do this intersection, instead of thinking of it as having to sweep, essentially, this whole square through here and actually do testing to see whether we overlap with these pieces, what we can do instead is say, let's pretend that we did shrink this guy down to a point. What would we have to do to these shapes to make it so that a point moving through them behaves the same way as a rectangle would move through the unmodified shapes? And the answer is actually very simple. It's just we would have to grow these shapes by this shape. So essentially what you can imagine is taking the perimeter of this shape and sweeping this rectangle around it, right? So you imagine sweeping this rectangle all around it, and we would end up with a shape that was like this, right? And you imagine me doing that here as well, sweeping that, taking this rectangle and sweeping it all around the outside and taking that outer boundary, right? And now we produce two new shapes, right? That actually, if you can see, you can actually see intuitively what it is. It's S plus R. They're rectangles that are S plus R from their center out instead of just S. We now have two shapes that if we raycast it against them would give us the right result. You can no longer pass through there. And you can see that actually as R gets smaller, if R was like that small, they would have still left a gap that we could still pass through, which is correct. So as R crosses the threshold of how big R would have to be to fit through here, it creates a gap or doesn't create a gap based on that. So what the Minkowski, that's called the Minkowski sum there. Excuse me. I believe technically this term is sort of not even a real term. I think it's usually just considered a sum, and you're either doing the sum with a negative or not. I don't know. It's a little odd, but Minkowski sum is the name for that. So, where does that leave us, right? What does that actually do for us functionally? Well, if you think about, oh, Krita, here it comes. Look at that. Oh, but it didn't, why didn't it use my background? What, guys, what's going on with that? It's supposed to clear to my background color, right? You saw it happen, didn't you? You saw that happen. Why did I get chumped? All right, hold on a second. Can I fill this with something? Can I do anything? Fill. What's going on here? Fill. What? Okay, seriously? This is just absurd. You guys saw that happen, right? And now I can't seem to undo. Why can't I undo? This program is fired. I don't even know what it's doing at this point. I feel like it shouldn't be that hard to just have a thing that draws. Okay, there we go. Well, that was disappointing. That was supposed to be the big moment, and the big moment was totally flaccid, is basically what happened. So how do we clear this thing? There's got to be some way to select stuff, right? How do I select just a region in this program? Does that select a region? That looks like it drew a rectangle. There, that selects a region. So if I select this region, right, I feel like I should be able to clear it. Can I not clear it? Clear. I don't know. How about fill with foreground color? I can't fill with foreground. All right, guys, seriously, this is just ridiculous. Unacceptable behavior on the point of the drawing program. Unacceptable is my opinion. How come I can't really do anything anymore, as far as I can tell? Like, I can't even do the old way that I used to clear stuff. All right, if that's the way you want it, I guess we got to make a new drawing. New drawing. And we're back. Of course, I can't apparently get the colors that I wanted either. This is just a disaster. This is the worst thing ever. I just want, at this point, I think I have to write my own drawing program for this stream, which is absurd. Like, okay, where'd that layer go? Does anyone see it? I don't see it. Where is my layer? I think we've got some kind of weirdness going on with the other ones. We have like a vector layer that it created. I don't want a vector layer, to say the very least. I want that gone. All right. So that's probably what happened here. We got some weird vector layer in the mix, and then we couldn't clear it. It was clearing that other layer. Lame. All right. Well, at least we got something working. Man, what an interruption. So annoying. Okay, anyway, back to the topic at hand. Now that we've got that straightened out, we'll clear this guy. Okay, so what I wanted to talk about before I was so rudely interrupted by Krita is that if you think about what happens here, right? If I have any shape at all, and I want to do this Minkowski operation, so I want to shrink this shape down to a point, and I want to expand this shape by it so that I can do raycasting on it as if it were just a single point coming against it. Again, I sweep the shape around the perimeter of this shape, and I get the result. So if you imagine putting a circle, right, and sweeping it around the perimeter, right, you can see that basically this plus this, right, equals this shape. It's a rounded rectangle, right? There's my new shape, right? So that's how you do the Minkowski sum, or how you can conceptualize the Minkowski sum. Now, that's a very complicated thing to think about because you're like, well, okay, great. Conceptually, that makes sense because I'm a human and I can just imagine sweeping a shape around another shape, no big deal. What does the computer actually do, though? Like, how do I code something that works that way, right? And the answer is, well, in one case, it's pretty simple, right? In the case where you have two shapes that are essentially the same shape, right? Like two rectangles, and you want to do the Minkowski sum, all you're talking about is taking the dimensions of them and adding them, right? If this one was r and this one was s, like in the previous example, then if I want to shrink r down to a point, I just have s plus r as my new rectangle, right? And that's done. So if there are two shapes that are exactly the same, it's actually pretty easy. You just expand the radius and you're done, right? But there's kind of a hidden assumption there as well, which is that those shapes also have to have, some way to easily parameterize them like that. But like for rectangles and circles, that would work, right? If we did circles, the same would be true. If you had a circle of radius s and a circle of radius r, and you added them together, you get a circle of radius s plus r, right? So that's really easy if you have that. But if you don't have that, it gets a little more complicated. Like, what about this rectangle case here where I've got a rectangle plus a circle? You can see that it makes a much more complicated shape. And so if we were going to do, say, raycasting against that, we would have to do very specialized raycasting to raycast against circles and rectangles together to make this sort of composite shape that produces the right answer no matter what you were raycasting at, right? And that's actually, it's not terribly hard to do even that, but you could imagine much more difficult ones that were like super crazy, like, oh, this is my shape, and I'm adding it to like this shape or something, right? And that's going to be this crazy thing with this swept around there that's got like another convexity here and whatever, right? So you can see that it would get pretty complicated. So there actually is a way that we can do operations like raycasting and those sorts of things against very complicated Minkowski sums, if we want to, which is called GJK, actually. Which is named after the people who this is one initial from each of the people who originally invented the algorithm. There is a general purpose algorithm called GJK that actually allows you to do essentially any Minkowski sum operation that you want to do in that way for things like raycasting or collision detection with any shape at all, as long as it's convex. So you can't quite do something like this without first breaking it into convex pieces, right? Which would be something like this. And that's actually pretty common in collision detection, to take concavities and break them into convex pieces, because operations on convex pieces are so much faster that it typically is better to just do 4 operations or 5 operations instead of 1 operation and do them on convex. So typically what ends up happening is this will becomes like sort of a workhorse that you use for the collision detection, and you just end up doing it so that you break all your stuff into convex pieces first. Now for our game, I don't know that we'll ever actually have all that many concave things. I suspect we'll have mostly convex things anyway. So this part might not be a problem, but we may need to implement this as our final collision detection system because we may want to do some crazinesses like polygonal convex objects, for example, and circles and all that stuff. And at that point, it becomes pretty difficult usually to conceptualize how you're going to do stuff with a raycast. So you typically want to do something that's GJK or GJK-like to do it. But for purposes of just what we need to do right now, we probably don't have to implicate. Okay, thank you. Krita. Oh, Krita. At least it's free. At least I didn't pay for it. So I guess that's one thing you could think of. You get what you pay for. And it turns out that's not very much. Okay. So basically, like, what we're doing right now, if we just want to do rectangles, like I said before, we already know how to raycast against a rectangle, right? So if we have point versus rectangle, we actually already know how to do that, right? And so if we want to, we can easily make the guy be a rectangle as well, and we can say, you know, okay, if we want to make this guy into a rectangle, no problem, we'll just take however big the guy's radius is and add it to the radius of the thing we're testing against, and we're done, right? That's it. So we almost don't have to change our code at all, thanks to Minkowski. Just to do a simple area version, it's pretty trivial, thanks to him, right? Thanks to Minkowski. And so you can imagine how we would implement this in code. It would actually be really easy if we want to give that guy some radius. Right now, right, he comes up here, and he can, you know, go through things really easily, and he interpenetrates through. And if we wanted to say, let's stop doing that, let's give him some more girth there. What we can do is just in the code. Why do I have another one of these as well? I have no idea what's going on with Krita right now. I'm totally lost. Okay. If I want to go into the code, which it looks like I didn't ever even open up my editor yet, so let's open up the editor. Let's see here. There we go. So if we imagine what we would do to our code here where we're testing all the walls, really we already sort of determined what the shape of the wall was by using min corner and max corner. And what we did is we took the tile side in meters and we divided it by 2 to figure out what the span was. So all we would have to do is just to min corner and max corner, instead of using this as the radius, like this is effectively our radius for collision, right? It's the tile map tile side in meters. Instead of just using that everywhere, which is what we were doing before, all we have to do is grow that radius now by however big we wanted the player to be, and the player suddenly would have that much area as a rectangle, right? So I don't remember what we set the player width and height to, right? We have some kind of a thing like that, I believe, that we set earlier. Not that it actually meant anything, but we actually did have one, right? So somewhere in here, we've got, there we go. So we've got an entity has a width and a height, right? So when we are doing that collision detection, when we're doing that, we have a entity, we have a width and a height for the entity. So what we could do when we do that radius value is we could say, okay, we've got a radius, we've got a width radius and we've got a height radius essentially, right? And for the tile map, it's the same in both cases, but in the case, and this is actually, I guess this is more of a diameter here because we're dividing it in half in a second. So this is really the diameter, right? So I've got diameter, width, and diameter, height, like so. So I can think about just going, okay, for the width, I'm just going to add that entity width in there. And for the height, I'm going to add that entity height in there. And that's the width and height that we said that the person was, right? And so I don't actually remember exactly what we were doing with that, but it's I think we were using that more for drawing, but I'm just going to use that for collision detection at the moment. And so now I believe that rectangle is the size of the collision area, or should be. Oh dear, what did I do there? That didn't work at all. Okay, I've made a slight error. I apologize. My bad. I don't actually know what I did there. So I said that it should work. Apparently I was quite mistaken. Hold on a second, let me see what I did wrong. So we have the tile map side in meters. We're adding that entity width and height. Let me step in there and make sure that I, and let me see what's going on here. So we've got the min corner X and the min corner Y, which is correct, right? Yeah, let me go ahead and recompile that and make sure, and let's step in there and see what I did wrong there. I believe that should have just worked, but it is fairly early in the morning, so I may just be delusional and there's a step that I'm forgetting here. So let's find out. Okay. So let's, there we go. So when we get into a tile that is supposed to be, that we're supposed to be colliding against, oh, right, never mind. I know exactly what the problem is here. So we do have another problem, which is that when we actually look at all of the tiles and we figure out what the minimum and maximum tile are that we're going to loop through, we do have the issue of looping through those tiles. We have to take into account the size of the entity because we may need to grab more tiles than we would have grabbed that we could be colliding against. Yeah, this is kind of obvious. I'm not sure why I didn't mention it before. Just wasn't thinking this morning. So if you imagine, what we were doing is we were doing a little iteration over the over basically the entirety of the tiles that were touched. We were looking at something where we were saying, okay, you know, let's say the guy moves from here to here. And we said, okay, what are all the tiles we need to check? Well, we just need to check the tiles into which that falls, right? But that's not actually true. Because if you think about it, once the guy has some area here, he actually could hit walls that are in tiles that are further away than that. So what we really need to do is look at this corner and this corner, right, of that, and say, what are all the tiles that those would overlap? And that is actually all the tiles that we need to check. So the reason we can tunnel right through stuff now is we're actually looking at things that we've already passed by them by the time we check them. We've already gone onto the inside of them. So yeah, so that's a fairly obvious thing. I don't know why I didn't think of that before we hit it. And so yes, there is another step, and that is the step. So I'm going to go back to doing this the old way because we didn't really need what I was doing before. And I want to also do some kind of assert here. Let's see. So I can actually move this loop back to the way that it was as well. We can actually do something like this, where we do min tile and max tile, right? Because we said that we're not going to allow wrapping anymore because that was just going to be too much of a pain to maintain. At least I believe it will be. So we're going to do something like this, where we just are back to the good old, familiar, easy way of doing things. So we basically have our min tile y, our max tile y, and we loop over them. Abs tile x is less than or equal to. Because this is always just easier to think about, and so I'm kind of glad that we don't have to deal with the wrapping anymore, because that was just going to be a huge pain. Okay, so there we go. And we need to make sure that we never actually wrap as well. So we probably want to do some kind of assertion. You know, something like so that we know that when we've wrapped min tile x, you know, something like the fact that these should always be less than, you know, some reasonable value, right? We shouldn't ever be getting the gigantic 4 billion ones here. So I'm just going to slap one in there so we know, because we haven't actually moved our world to the center yet. That's something that we would like to do. And so just in case we forget and do some stuff off the edge of the screen there, I want it to warn us so we know what happened and we're not like, what's going on? All right. So assuming that I do that, I just want to make sure we're still good here. Okay, there we go. Assuming I do that, I would now like to go ahead and account for basically that player size, this thing right here. So what I want to do is I want to make a min player p that's basically what I really want to do is I want to extend these by however big the entity is in tiles, right? So after I do min tile x, max tile x, and so on, I want to take like the min tile x and I want to subtract it by the entity tile width, right? Basically, I want to do that, and I want to do the same for the min tile y, right? I want to expand that rectangle out like I drew in the diagram. So I want to just go ahead and do that. So what I need to know is I need to know how big the entity is in tiles, right? Rounded up, basically. So what I want to do is say, essentially take the ceiling of that. Let me take a look and see. I don't actually remember if we ever did ceiling. Did we do ceiling or did we only do floor? Let's see, floor. So we did floor, but we never did ceiling. So I would like ceiling for this operation, right? Ceil F. There we go. Again, that should be something that we can get to be relatively in line eventually. So what I want to do here is say, okay, well, the entity tile width, I know his width in actual, in like meters, right? I know his width in meters, but I want to know what his width would be in tiles at this point, right? So I want to know, and there's two ways I could do this, right? I could do a slightly more conservative bound by putting it actually into the computation here and then rounding out the tiles, but I'm not going to bother with that. I'd rather just do a slightly more conservative thing for now, and we'll let that be something to worry about in the final collision detector. So what I want to do is say, well, whatever his width is, divided by the tile side in meters, and I guess, to be honest, I don't really need, now that I think about it, I don't really need the ceiling, so maybe I shouldn't bother putting that in there. I don't know. We'll leave it in there, just in case. But all I really need to do is say, okay, if I have the entity width and I have the tile side in meters, then I can divide the width. Sloppy drinker. I can divide the width by the tile side in meters, and that will give me how many tiles he would expand by, right? And so I can take the ceiling of that, and I'm expecting that to generally be 1. But, you know, if you had like a real big entity, you could imagine it spanning multiple tiles, and then it might be a wider expansion. So I figured I'd just do it the way that we would, want to do it. So we're just going to take a look at that and say, okay, let's go ahead and get that out there. And since this is an actual integer function, so what we should do now is if we step in here, we should see that box expand by that min tile x and min tile y when we go to do collision detection. So let's take a look at what we computed. Yeah, 1 and 1, which is exactly what I thought it would be. And then when we've got our min tiles and max tiles, they look like they're coming out correctly. So now we're going to expand those, min tile x, min tile y, max tile x, max tile y. So we're going to expand those out so the mins get smaller, the maxes get bigger, which is what we want. And now we're doing it over a wider radius, right? And so I believe that should solve our problem. And it does. Of course, we do have one more thing to solve, which I'll talk about in a second. So I think we're basically, this looks like it's actually working exactly right. We should also probably stop drawing the walls this way because the walls are actually bigger because remember I took 0.9 of them away so we could see around them. So it looks roughly correct. All right. So, ooh. Very sticky there, which of course is, again, because we haven't actually dealt with what happens when you actually hit the wall yet. So one thing that's happening now, though, that you can notice is when we collide against this side and when we collide against the other side, that's very sticky. I wonder why that's so sticky. That's weird, right? Don't you think? That is sort of... What's interesting about that, I wonder if we have another bug, but this is what I was expecting to have happen to our collision detector before, and I wonder if it's just because all of our stuff was tiled aligned that we weren't having that happen. It's just kind of like, the stickiness was what I was expecting to happen with the old collision detection, and that I was going to talk about how we would have to get rid of it and so on. But anyway, so I feel like something bizarre is happening there too, though, because I believe we're still using an epsilon when we set things away. So I think we've just got a straight up bug in there as well. Because if you remember, we're actually placing the guy a little bit away from the wall. So when he tries to go the other direction, he should not actually still be hitting it. so I do think that he shouldn't actually be getting stuck in that fashion, even at this early stage with the collision edge. So I think we have another bug in there that I'm not thinking of, but I'm not sure exactly what it is. So we'll have to think about that in a second. So anyway, point being, what I was going to talk about first is the fact that you'll notice we're drawing his height off of this pixel here. We're drawing his height offset from where he actually is, right? So his center point, where we're drawing this rectangle, we're drawing him as if the whole height comes off of that bottom point, right? And so what happens is, when I hit the bottom edge, I stop where I would have stopped if the rectangle was done this way. And of course, that's exactly what we would expect to happen, because the collision detector is treating it as if it's a radius value out from that center point. So what we actually want to do is talk about just this area, or whatever the area is that his collision is going to be in. We want that to sort of be the center of where he collides against, right? And we don't want to start to think about it in the other way. So the entity width and height is actually going to be about that, around wherever the center is of his collision, and what we want the bounce to be around there. So I want to start drawing him that way, because that's the way it's actually going to work. If I go take a look at where we're doing that drawing for the entities, you can kind of see what I mean by that. We basically have a thing where we do the player left top, and you can see that we subtract the whole height. So what we actually want to do is subtract half the height. So now it's centered just like the old one. And you can kind of see that is more the rectangle that we're talking about, and that one stops the way that you would expect it to stop, and so on. And so now we're actually correct, but that is not the size we would probably want to use for that entity width. So what we probably want to do is make his entity height. So we probably want to do is make his entity height a little bit better. So I believe that's an initialized player. And so this is not really the height, it's really his collision height. And I don't know if we want to talk about his actual height as well. So we may want to actually talk about dimensions in a slightly different way. So I'm not sure how we want to talk about this eventually. So for right now, we'll say that it's just going to be something like, 0.5 and 0.5. I don't know, how big is that? Let's find out. That's a little bit, oh. That's not what I meant to do. That's what I meant to do. There we go. Yeah, so that's a little too small. Let's make it still a little bit wider. So maybe his width is about 1 and his height is about 0.5, because of just the way the game's perspective is. That's probably a little bit more like what you would expect the shadow of the player to be. And so off he goes through here and so on. And he can hit things like we would expect. Okay, so what I'd like to do now is, before we go ahead and do the gliding, our area collision is working properly. But before I go ahead and do the gliding, I want to figure out why we're getting that sticking problem, which is bogus. Okay, there we go. Yep, so we've got our area collision back. And as you can see, with Minkowski makes a lot of things much easier than they would otherwise be, because you can basically use the same code that you would have used for something else, and you just fiddle with the inputs a little, and all of a sudden you get something great, right? That's what you wanted. So you can also see, though, and this is why I say that eventually we want to do circles, you can see how with the rectangle, I kind of would stop here, and there'd be really no gliding I could do, whereas with a circle, it would kind of roll me off into inside. Once we actually implement the gliding code, which we haven't done yet, right? But you can see that that won't actually improve. So yeah. So what I want to do is I want to take a look at the sticking now. So what I want to do is know what's happening here, why I can't get out of here. I want to actually just look at the code directly and find out why we're getting the sticking, because I feel like with the epsilon, we shouldn't have been able to do that. That's obviously not true. And so, yeah, so I'm going to go ahead and set our loop point here. So I'm going to do a loop point set. I'm going to move out for a while so that I know that I'm trying to push outwards, and then loop it. All right. So I'm going to go in here and say, let's go ahead and step in and see what's going on. So we're here. Let's go ahead and step in here. So we're basically only checking two tiles. We're checking the tile that we're on, and we're checking the tile below us. Basically is what's happening there, right? If you look at the min tile x and the max tile y and max tile x, let's take a look at the DDP, make sure it's something that we want. So that's not actually a DDP that I want. I wanted a DDP that was going to be actually trying to move us down, right? Why is my DDP always so tiny? Obviously, the collision detector can't move us anywhere if the DDP is always super tiny. What is the meaning of that, people? What is the meaning of it? Why is that happening? I don't understand. I recorded a thing where he was definitely moving down. We should be able to get a DDP where he's actually moving himself down. But it doesn't seem like that's ever happening. Let's go out and see why not. Okay, game update. Let's see. So, no one... What? What is the problem here? I do not understand what's going on. There we go. Okay, so I guess it just stopped in the middle of one randomly. All right. So the controller is not analog. Ended down. So ddp.y is -1. ddp.x is 1. We move in here. See what we've got. ddp is 1, -1. So we have to renormalize. We get the right thing. Multiply by the player speed, which is good. What? His velocity was negative that? Did you see what I saw there? How did his velocity be equal to negative what it was? What is going on here? We're not even updating the velocity, right? Oh, is it just... Oh, are we just seeing literally that fact that the velocity is never getting updated because we haven't actually gone and done any work to correct it? That seems odd, though. Why would that be the case? I guess I could imagine that being the case. Let's just see if that's true. I'm going to go ahead and test that just to make sense, because that's pretty interesting. I guess if we had just gone and implemented gliding, we would have gotten rid of the problem. But yeah, so in this case, when we did the tmin there, when we sort of looped through here and found it, basically what we're saying is if tmin is less than 1.0, then we would want to go ahead and zero that velocity out. And that would just stop him entirely in his tracks, right? Is that really the problem? That seems odd, but I guess it could be. Let's find out. It does look like that was indeed the problem. Well, totally fine. That's fair. All right, so I guess that means we really didn't need to debug that, because if we'd just gone ahead and finished the gliding implementation, where we were going to update the velocity for our new collision detector, it would have just worked. But hey, it was good to inspect anyway so that we know what it was and aren't, worried about it, I guess. So that's fine. So we're now in good shape. We've got the area working fine. So all we want to do now is implement the gliding. And to implement the gliding, we just have to do the same thing that we did before, right? Where we update, basically using that same idea here, where we did our sort of our bounce equation, right? Where we actually take away all of the bounce velocity and just leave the remaining velocity, right? So if we want to do that, we still have the exact same code essentially, but I'm going to make it a little bit cleaner. So basically, if we go down here, I'm going to say that after we do this test wall bit, I'm going to go ahead and say that we got to update our velocity instead of doing it this way. And what we're going to do is we're going to do this inner product thing. You notice that the way that this is set up, it's saying that the existing velocity, we subtracted away the part that we didn't want anymore of that velocity, right? And by doing the way that we did that is we used an inner product with essentially the normal, if you remember, the normal to the wall that we hit. And what's nice about this equation is this actually works whether or not you hit a wall, because if we just set the normal of the wall to be 0, 0, this term would evaluate to 0, right? So what we could do is just say we always update the velocity with whatever wall he hit, and then we just have a wall normal right here that we're going to track. So we have wall normal, and it's going to be equal to 0, 0 always, right? And then we're just going to update that along with our tmin. Actually, trying to think of how I want to do this. Because I don't think this thing really knows what the wall normal is. So let's do it this way for now. Right? Wall normal equals whatever the normal would be. And so we're basically just doing the exact same code that we did before. Only this time I'm setting an arbitrary wall normal. So we could expand this code, I guess, to use walls that were not. Like, nothing in the code now really counts on the fact that the walls are horizontal or vertical, except our sort of not particularly good solution up here to testing the wall. It's this code right here would have to get a little bit better to handle a slanted wall, but that's about it. So what I want to do is say, all right, we can return whether we hit or not. So hit equals false, and in this case, hit equals true, right? So we'll return true, return hit. And now I'll just go ahead and set the normal to what I know each of these wall normals to be, and off we go. So in this case, I'm testing against the min corner x, so that normal would be in that direction. For the max corner x, it would be in the opposite direction x. Same thing here and here, right? And so I believe that should update our velocity correctly now. Excuse me. So we should be able to glide if I didn't mess it up, which I may have. And it looks like I did. Did I forget to... what did I forget to do here? So wall normal... I feel like... Why is he stopping there? What did I mistakenly do? There's one thing we need to do in addition to this, but I feel like I should have glided properly just from that. Yeah. Let me verify that it's not the other thing that we need to do first, but I'm pretty sure it's not. Oh, okay, so it actually is. All right, never mind. I take it back. Okay, so now we're at the situation. He actually is gliding properly. I take it back. You can actually see him gliding properly there. The problem is we have to do the final thing that I said. If you remember when we talked about... I thought he was coming to a complete stop. He actually isn't. He's only stopping if we continue to try and go to the wall. So we're at the point where we can finally fix the final problem that we had, which is what we were talking about before, where it doesn't continue the move after it does this. And so remember I said we have to do a loop where we try to correct the velocity during collision and keep trying to move him for the remainder of the time step, right? So that's what we want to do now. So basically what we need to do is say, okay, we now have to go ahead and do this sort of test where we're going over things, this part here, right? We have to do this for some number of iterations so that we can say we've got our, well, actually I don't need to call it iteration index, it's just iteration. I think I said 4 would be how many we do, because we want a bounded number. We don't want to just keep going until it's 0. So basically what we would start out with is we'd have a t remaining, essentially, right? That starts off at 1.0, which is to try and do the whole move, right? And what we want to do now is say, okay, we have this, that player delta, which is the value that we computed. That's how far we want to go, right? So we have that player delta, and the player delta, we're going to start off by saying we have all of the player delta to try and account for. We want to try and move him the entire player delta distance, right? And then when we do the code for hitting the wall, we say, okay, we start the t-min, meaning the minimum distance that we could go along it is, and I guess in this case we could say it's 1.0, right? Excuse me, is how far we want to go. And then when we finish, we know how much of the how much of the step we've actually used, right? We know, I'm trying to think of how to say this. We know once we take one of these steps, we know how far in t we've gone, because at the end we have a new t-min, right? We've updated t-min to be the percentage of player delta that we've used. Does that make sense? So essentially our t remaining, right, we subtract away whatever the inverse of that t-min is, because essentially we've sort of said, and you know, I guess we could do it. We could do the math. I'm trying to think if this is a good idea or not. We could actually do the math such that we actually are always just using t-min if we want to. Maybe I'll try to do it that way. So we start with our t-min at 1.0, which is we can move the full distance along the player delta, right? And then we go in here, we update t-min to be how far we actually have moved until we hit the wall. And then we try again to move, you know, with the new t-min, and we keep reducing it. And if t-min ever falls to 0, so basically like, and t-min is greater than 0, if t-min ever falls to 0, we've done the entire move and we're done, right? So that's totally fine. So basically, what we want to do is say if we didn't hit anything, right? Because each time we update this, our t-min will go down to the distance that it went. Now, you know what? Just thinking about this, the sense of it's just wrong. I just don't think I can do that. Yeah, I can't. Sorry, in my head, I just can't figure out a way to make that work. We'll see after I write it with the two variables. We'll see if there's a way to do it entirely in t-min. I don't know if there's or not. So I'm just going to say that we have some time step remaining. We have the t-min, and we basically say how much of the t-min did we use. And then at the end, we take t remaining, and we subtract from it whatever was left of the t-min, right? So basically, if we got to go the entire if t-min was the entire way, so it was 1.0, right? We would subtract from it. Sorry, no. If t-min was the 1.0, we'd subtract the entire thing. Yeah, so we always subtract how far in t-min we actually went. Yeah, that's right. So, okay. So what we have to do here is say, all right, here's our player delta, right? And our t is how far along this we've gone, right? So when we do our t-min, what our t-min tells us is where we stopped along this line. It tells us a percentage, right? From 0 to 100%, right? So it ranges from 0 to 1, where we stopped. If we went all the way to 1, right? If we went all the way to 100%, we're done. So we always take whatever our t-min comes out and we subtract from how much we had of a t to begin with, right? So in this case, right, our t-min is, when we first start out, our t-min could be 1.0, and we could go the entire way, and we're going to stop when the t remaining gets to 0. But on subsequent times through the loop, we could just say we have only however much t we actually had left to use, right? And then we go from there. I believe that would work just fine. And then what we want to do is say, well, when we do our updating, right, we need to do the updating every time, right? Because every time we hit a wall, we need to update the player location to that point, right? And then we need to update, excuse me, and then we need to update the velocity to get rid of whatever part's part of the wall normal. But we have to do the same thing, right, for our player delta. So our player delta has to be chopped so that it's not trying to go into the wall anymore either. So basically the exact same equation where we do that bounce, we have to do that for the player delta as well, right? So we get rid of whatever portion it was trying to go into the wall. Now remember, this offset is somewhat expensive. So really, we could decide just not to do that offset, the player positions thing, right? We could decide to do the player position thing outside here and have a thing called total player delta, which basically says what part of the player delta actually got used and we'll sum it. So we'll say total player delta, right, is going to add whatever the step was that actually was used, right? And then what we need to do is we need to update that player position. So this thing where we do the rel old player. Oh, well, I guess, never mind. So I guess since that is something that we're actually still using inside the loop, we might as well keep it this way. Since we're still using the entity P. And so old player P, I believe old player P is never, I don't even actually know why we still have old player P. We're just talking about entity P really this entire time. And that's easier to update. So I'm going to go ahead and say that we do it this way. And I might get rid of old player P, since old player P is not actually used anywhere, as far as I know. Okay, so it's used there. So we just want to snap it once at the beginning, so that's fine. I'll leave it around. All right, so I got to update the entity's position with this new position. I got to update the velocity with the new velocity, and then I got to update where we're trying to go to with the new amount that we're trying to go to as well. So let me take a look at that. We don't want total player delta. That's just regular player delta now. There we go. And so let's see how that does. There we go. So there's our skating. Oops, still getting a problem there. That doesn't look quite right. So we still got a bug, but we're almost there. Just not quite. Just not quite there. All right, so what's our problem here? We did our offset properly. Oops, my laptop screen has gone to sleep. That's not going to be very good for reading the Q&A, certainly. Let's try that again. There we go. And okay. So what we need to do now is figure out what I did wrong there. We're updating. What are we updating here? So let's make sure I've got everything correct. So we've got our absolute tile z. We've got that. We've got the centered tile point is being computed properly. Yes, we get the tile value. This is the entity width and height. That's based on that. That's all correct. We're subtracting the entity p, which is the thing that we are updating, so that's good. And then we do all of our testing. We get our wall numbers back. We update the entity p by whatever the player delta was that we computed. We remove the part of the player delta that would have gone against the wall normal, which I believe is what we wanted to do. And we update the velocity of the guy as well based on that wall normal. And then we take away whatever the amount is that we stepped forward, which seems... I think... Okay, so I may be double counting that. Let me think about that. So I think I'm double counting that because if I were... Although that shouldn't have really been in effect. The second velocity should have worked either way. But yeah, so you would still go the whole player delta because we are accounting for the fact that the player delta is getting smaller. So I think actually technically this should always be 1.0. And then when we subtract it out, it's just we subtract whatever proportion of the player remaining we used, if that makes sense. I believe that's correct. Yeah. So I think that was our only bug. Not sure if you saw what happened there. So I'm not sure we're still entirely correct. I'm a little bit nervous. There's a weird thing that's happening there, which is, I believe, because our epsilon's too high. Like you can sort of see, I don't know if you can see it kind of when you go, he moves a little closer. You know what I could do? I could, we had a key, that's what it was. I could make it bigger. So you can kind of see he squishes into the wall a little bit, and I believe what's happening there is our epsilon actually stops him before he would actually get to where the wall is. And so as he moves in a slighter fashion, he can actually get a little closer to the wall. So I think what we want to do is we want to make our epsilon tighter than it was. So I'm going to say, so the epsilon, the problem is the epsilon is only in player delta space, which is not great. I don't think that's particularly good. And I feel like we should probably get rid of this epsilon eventually anyway. In the real collision detector, I think what we'll do is just not have it, but that's a separate issue. So let's take a look and see if that's a little bit better. course, that's too close. Yeah, you can see why you don't want to have these epsilons, right? So we want to do something that doesn't actually have to have the epsilon. This may be good enough just for now because, like I said, we want to do the regular collision detection. We want to do it a little differently anyway when we're actually going to do it. So it's probably better to deal with those things there, but there is that little weirdness that I don't love. It's kind of hard. You can see it, right? You can kind of see it. Yeah. We also have that problem of like the player's velocity as it gets clipped. It's causing his facing direction to be like changing very rapidly in when he actually hits things. So we probably have to pick his facing direction on something a little more stable as well. But yeah, you can kind of see how he scoots into the wall a little bit. So that's just lame right there. And so I think now that I think about it, the fact that this epsilon is in the wrong space is really most of the problem there. So thinking about what would have to happen for that, essentially, so when we actually do that T-min, you'd have to actually say, you know, how big is the player delta, and you'd have to adjust based on that. So I'm not sure exactly what the best way to do that would be, because if the player delta is really small, then you would want to use a really small delta. So you want to actually make that minimum a little bit different. So what I could do is say that the epsilon's not going to happen here. You know, the epsilon's going to be happening outside, and that would be better, but still not fantastic, right? So essentially, you know, in the case where we actually did hit something, so I say hit equals false. In the case where we actually did hit something, I could apply that epsilon outside, which is, again, not particularly great. Having an epsilon at all is not good in general, but I could say if hit, and if in the case that we hit, we also know that we only need to do these when we hit, so, you know, we could do something like that, so that we break out immediately and don't have to do the test. I don't know if that's probably not really worth it. But we do know, for example, that we don't need to update any of these unless we actually hit. So okay. So in that case, if we actually did the hit, then we would do... yeah, but I can't quite do it that way, I guess. So, all right, never mind. Never mind. I thought we were going to be clever, but we weren't. So in the case where we hit, I'll just say this equals that epsilon there at the end. And the only reason I'm thinking that that's the case is because now I can actually see whatever our t remaining was. Our t remaining we could actually use to boost that epsilon up to larger values based on how far we thought we were moving. Because I believe that most of it is... Well... I'm not actually sure. No, you know what? Why did I do that? That doesn't really make any sense. Because there really isn't that much information that I could use outside. It's still the same as the information that we have in here, right? I could just do whatever I was going to do, I could do in here. So I'm going to leave that way for now. Because I don't see a super easy way to fix that without doing something better. Because again, that epsilon is just going to be... The problem is when you actually do hit the wall, you've got that epsilon that wants to be a little bit different. Yeah. See, that's just bad behavior right there. You can kind of see... I don't know if you can see that well on the stream. I believe Alt-1, I believe there was some way we had that was supposed to zoom in while zoom in is running. Control-1, maybe? There we go. Ooh. I guess that doesn't work, unfortunately. Can I zoom in there? So unfortunately, while I'm zoomed in, I can't animate. So I guess so that zoom effect doesn't really work for this. But you can kind of see what's happening as I go in there. And I don't know, that might just be another bug we could look at in a little more detail. But basically, I want him to stop directly on the wall and not have that little stuttering behavior. And I guess I'm not entirely certain that that's the epsilon. So I guess what I could do too, you know what? I'm going to go into the Q&A a little bit just because I feel like I can. I want to just look and see if there's another bug in there. I just want to watch what the behavior is that happens when he hits that wall. So I can do that actually pretty easily because I know that he's going to hit this wall, right? That's the wall he's hitting. So if I want to, I can stop just when he's about to hit that wall, right? Which is right here. So let's take a look at what actually happens when he hits that wall. None of these other walls should hit, presumably, because he's just hitting that one wall. Yep. And so let's see. What's our team in? Our team in is 0.75. What's our player delta? Our player delta is negative 0.2, so he's trying to move that much, and he's basically not moving in y at all, right? It's an e negative 0.6, so that's a very tiny value in y. All right. So when I update my entity P, I'm going to move him by the amount that he was able to move, right? Which is 75% roughly of the way to the wall. And so we go ahead and do that. Now, where does that leave him? The player position, let's see, entity P. Where does that leave him? Oops. Versus where the wall is. I'm going to delete some of this stuff so I can start fresh. Where does that leave him? So we have tile mapped tile side in meters, right? That is, oops, divided by 2. That is about 0.7. And so we're going to do our offset of the player now. So we do that offset. And we get an x of negative 0.19, which is actually nowhere close to this, which is fine, because we also have the player width to account for. So what's the entity width? The entity width is 1, so that's 0.5. So that's stopping him right on the. That's doing exactly right, is basically what's happening. So I think we just have another bug here. Okay, so entity dp. We're updating the velocity of the fellow himself. We have clipped his x velocity away, which is exactly what we want. We are taking the player delta, which is this right here, which is how he's trying to move. That is clipped as well. And we are taking the t remaining, which was all of it, and we're reducing it to just what was left after the move, right? And so I think that's what we were expecting. So that's fine. Let's see what happens now. So now we got a team in of 1.0 again, and we're going to see whether or not we collide with anything. Now my understanding is we should not collide with anything, right? Because we are free and clear at the moment. So I feel like if I were to set these, we should not hit one of them. And we don't. So that's good. That's behaving as we would expect it to. So now we have to do our offset again. We have the player delta. The player delta has no x component whatsoever. And the dp, let's see here, entity dp also has none. So they should really not change much at all except in y, right? And that's fine. So there we go. And player delta does not get updated. Tmin was 1.0, so now t remaining is 0, and we should fall out of the loop. Yeah. So we did exactly what we thought we should do. So now the question, I guess, is just the second time through, I guess it was wrong. Must be, because that is apparently correct. That all looked exactly right to me. Nothing bad happened there, right? So what is happening with that nonsense? So in order to fix that, again, I'm going to lean on our looped live code editing, as I so often do. I'm going to set that up and then do this, right? So now he's just constantly careening into the wall, and that'll make sure that I can basically debug the exact case that's happening, right? So what I'm going to do is I'm going to set that breakpoint again. I'm going to set that breakpoint here. When he hits the wall, I pretty much believe that that loop operated as it was intended, right? So it comes out here, and does its update. Off we go, right? Does its little dance for the facing direction, which is fine. And yeah, and I think that should be it until the next call to move player. So let's see what happens in that call. So in the next call to move player, we come in here, and our DDP should again be trying to accelerate him into the wall because I was pressing straight into the wall. -1, that's exactly what we would expect. We go through and we compute our stuff, as it were. Min tile x is 1, min tile y, max tile x is 1, max tile y. Believe that's correct. Oh, is that correct? Yeah, okay, because we're about to expand it by the width of the guy. Yeah, so we're checking everything. Yep, so that's fine. So now the question is, we should immediately, again, hit this wall, right? That's what should happen, if I'm not mistaken. Oh, and we do not hit the wall. We don't hit the wall at all. Why do we not hit the wall? Is it because our velocity was not big enough yet to hit the wall? That could be, certainly. That might be it. We may have stopped just short of where the wall is, but I feel like we were right on it. So if that's the player delta, why didn't that hit the wall? Where is the wall x would be the real question. Unfortunately, it's kind of hard to figure out what that value actually is. So all right, so let's go ahead and say, what is the abs tile x and abs tile y of that guy? So let's do this again. Run. Go ahead and run. There you are, my friend. So I'm going to go ahead and stop it in there, and I want to see what the actual position of this wall is. Oops, I should make sure that we're actually looking. Okay. So what is the wall coordinate here? What actually is the max corner x that we're stopping at? It's 1.25, right? 1.2005. So let's find out where we actually move ourselves to when we decide that we hit that wall. Where are we? So we're at 1.25 relative to the tile. We are -2 away. And what's that tile side in meters, right? Tile side in meters is 1.4. So that basically, oh, and I guess yeah. So it's a little bit confusing just because since we do everything relative in tile space, the 1.2 is how far away from the tile you would have to be. And I'm not sure exactly where this guy is relative to that right now because that's kind of a hard computation to do in one's head. But, so if the max corner x is 1.2, then that means if between two tiles, right? If between two tiles is 1.4, then basically he should be 0.2 away from his current tile, which is exactly what he is. So he should have hit the wall the next time around. And the fact that he didn't hit the wall is somewhat troubling, I believe. So yeah, I think we're back to my original thesis, which is we've got a bug. Or something that we don't, a subtlety that we don't understand. This is not a problem with the epsilon, really, this is a problem with the code. So if I come in here, and I'm going to test this wall again, what I want to do is I want to take a look at what happens when we're supposed to hit that wall. So what I'd like to do is say, okay, let's figure out which abs tile x and abs tile y we're on when we do hit this one, right? Let's figure out which one that is. So abs tile y is 5, abs tile x is 0. So abs tile y is 5, abs tile x is 0, right? That's what we're looking at for the one where he actually does hit that wall. And so what I will do now is I will let him hit the wall in that way that he likes to do. and then I will go to the next time round, and I'm going to step into the case where he is supposed to be interacting with that wall. Style X, abs tile Y. So I want abs tile Y to be 5, so we're not quite there yet. We got to go through these two X's first, right? X is 2. Let's finish that up. Let's see. Oh, no, I missed it. The so slow iterating watch window is so frustrating. Ah. All right, let's do it again. Thank you, Visual Studio. Like, apparently it's an unsolved problem in computer graphics to update the watch window when I hit step. It's just so ridiculous how bad it is. All right. So we've hit it once, and now we're going to go again, right? And now I'm going to go ahead and run in here. So that's 0, 4, 1, 4, 2, 4, 0, 5. So this is the one we want to know about. We come in here, and let's see. So we've got our relative player location. Let's see what that is. Our relative player location and our min corner, our max corner. Let's take a look at what all our values are here. So his relative position is apparently higher than what I thought it was. He's got a little ways to go, but it looked to me when we actually did the computation before, it looked to me like he didn't. So what is going on here? What's the issue, if you will? What's our test tile P? What's our test tile P? It's 0, 5, 0, and 0, 0, which is what we would expect. And what's our player, or entity P? Entity P. What's that at? Or offset. So that's a different offset than I thought we ended with before. Right? Am I imagining things? I thought we ended with a totally different entity P than that last time. All right, let's step through it one more time. So there he's going into the wall. Which one am I going to stop at? I'm going to stop him here. So there I've hit the wall, right? And now I'm going to do my update. Step to here, update. What's my entity P? That was the entity P we were supposed to get. So what happened to our entity P? Why did our entity P, did it get changed in the second time through the loop? Because it shouldn't touch the X, right? So what happened here? It did touch the X. It did. What? Ah! Oh, the bugginess. Oh, did you see it? Oh, it's so awful. I forgot. I said I was going to get rid of old player P and I didn't. Oh, the pain and suffering. You saw it, didn't you? Oh, man. Boy, I'm glad I stepped through that. That was a good one not to leave in there. Hey, look, it's perfect now. Oh, that was terrible. That was terrible. It's coming out. The owl is coming out, people. That was a bad typo. And I almost left it in, too. I was like, it's not the final collision detector. Well, it's not the final collision detector, it's true. But you shouldn't leave that garbage in there. That's just awful. Oh, that was bad. All right. Looks like we're fine now. No more cause for alarm. I wasn't happy with what was going on in there at all. That was just bad news. So the other thing that I was thinking about is I don't know if we want the acceleration to determine which way the guy is facing, because it's a little weird right now, the way that it's working with the velocity, but I don't know. All right, so I'm glad we pushed through that. We can go ahead and actually go to the Q&A now. Wow. Okay. So yeah, that took an extra 20 minutes of debugging time to find one typo. Oh man. But that's what you get for putting in typos in your code. So okay, we're pretty clean now. I don't think we've got any more problems with that. And hey, it's a lot easier to skate through now, even with a rectangular collision. It's way easier to skate through those doorways, which again is why sliding is so important. You don't think about it that much when you're playing games, but being able to slide smoothly along walls is like really important, right? It's what makes it fun and easy to play a game and not feel super janky. So it's super important to get that slide in there. So it's worth the effort, trust me. So anyway, and it'll be even better when we have a circular dude, because then the normal that you're pushing off on will sort of help you slide into doorways easier, better as well. All right, so I think we're all good. Let's go ahead and go to the Q&A. Please prefix your questions with Q:, so I will be able to see them. And please keep your questions stuff we've done on today's stream or on previous streams. Yay! Glad we pushed through that. Why is the hero's head 1.5 meters in diameter? I feel like it shouldn't actually be quite that big. So like I said, the hero is too big right now. He is going to get shrunk down a bit, but he's a bit anime styled, as you can see. So his head is going to be ridiculously large compared to everything in the world. I'm a web developer and was taught not to have more than a couple hundred lines per file. Why isn't the game split up into smaller, excuse me. Oh wait, sorry, I skipped over a question there. If I recall right, then in a prior episode you were talking about how the Minkowski difference is a good solution for finding collisions only between convex polygons. Can it also be a good solution for concave polygons, or do you have something else planned for that case? Also, if you're planning on using Minkowski differences for concave collision geometry, is it also good solution in 3D, or are there better alternatives to handle the additional dimension? So the Minkowski stuff works the same in 3D as 2D. It's dimension agnostic, which is really nice. And the way that pretty much everyone universally, like in every game I've ever heard of in the history of time, handles convex collision is to break them up into concave pieces. That is almost always the solution. So basically what you do is you always just use convex collision, and you break up concave things into convex pieces. Because you can always take any concave shape and with enough splits, split it into something convex. So that's how that works. I'm a web developer who was always taught not to have more than a couple hundred lines per file. Why isn't the game split up into smaller, more modular files? So two things. One is that files have nothing to do with modularity, right? So modularity is about whether or not the functions in something are able to be called separate from other functions. That's what modularity, like modularity is about reuse. It's about whether or not I can reuse a particular thing. Obviously, I'm only doing one game here, so I don't care about linking to other games, but I do care about using stuff in multiple places. And so really modularity is about what I break out into functions. It has nothing to do with files. Files are a purely arbitrary construct, right? The actual code itself doesn't care about files. Files are meaningless. And so really, you should never think about how big a file is unless it's something that you care about in terms of legibility. So to the extent that I care about files, I only care about them in the sense that I like to look at two things side by side. So the only real thing I do with files is I say I like to split stuff apart when I want to be able to look at one thing on one side and one thing on the other side. That is the only thing that matters for files for me. If it wasn't for that, I just put everything in one file because it'd just be easier to keep track of, right? It's only in one file. You don't, when you want to copy the source code around, you copy one CPP, right? That'd be way better. So the dogma that you have to break things into lots of small files, I would just say, what's the benefit? What are you possibly getting out of that? You know, that because the compiler doesn't care at all, right? And so what is it that you think you were getting out of that? You know, what is it that you wanted to get out of that? And if there was something valid that you were getting out of that, could you get it another way? Would be my thing, because I don't think the huge file proliferation is a good thing. Plus, we also use a Unity build here because the more files you try to push through the compiler, the slower it gets. That's just the way compilers work, unfortunately. So having monolithic files actually helps there as well, but that's a separate issue. Is the alpha channel in the art assets created by the artist, or do you create them with a tool? Alpha channels are generally automatically handled in the art package. So basically what happens is when the artist draws, it fills in alpha as well as color. So when they draw, you get the alpha channel plus the color automatically. That's how that works. So it's already kind of in the source assets. How many years since you started doing games? I mean, I think this is really, really hard. Yeah, I mean, this is a more advanced, obviously this Handmade Hero is showing real game programming. It's not showing beginner game programming. I am walking through every single thing that we do, so in that sense it's beginner, but we're not pulling any punches. Like, we're actually looking at the actual stuff that the CPU has to do to run a game. We're not just like saying, oh, instantiate object and let Unity like figure out the rest, right? And so, yes, that can be kind of difficult because there's a lot that you have to learn. But you should learn a lot if you want to be an engine programmer, right? If you don't, then you can kind of just gloss over this stuff, which is fine, right? Handmade Hero is still probably useful because you can see all the stuff that's involved and maybe you don't totally understand it, but at least now you know. And so you'll be better when you're programming with other things. But yes, it is difficult. I don't pretend that it's not. There's just a lot to know. It's one of the reasons that there are so few game engine programmers out there, and fewer still good ones, is because it definitely is something that takes a lot of study and it takes a lot of practice to be good at. Orlando Bloom, I've never actually done this kind of collision detection. I always just hoped the frame rate would stay high enough that the velocity would be smaller than the collision size. And that's totally a valid approach, right? You just have to actually go ahead and make sure that's true, right? And it does put bounds on the sizes that things can be. You can't make sizes too small, or you have to start subdividing your time steps. But you can do that if you want to, right? But it's not that hard to do it this way. So, you know, basically you can think about it. Here's one way to think about it. Iteration will happen, right? Iteration will happen. So you have a choice of where that iteration happens. One place it could happen is in frames. So the way that your collision detector works is it's essentially each frame is an iteration of the collision detection, right? And that's what you were just talking about. Another way it could happen is by subdividing your time steps, right? So you could say, well, these are my frames, but I know my collision detector needs to be able to detect objects that are smaller than the velocities on these frames, so I'm going to subdivide it and do a couple iterations of the physics per frame, right? And that's one way. This is more efficient than this in some sense because it means that for the same collision size, you're doing less work in this case than you would be doing in this case, because in this case, your frame rate itself has to be this high to be as robust as this is as a frame rate that is much less, right? And then the final way is the iteration only happens inside the collision system. So the physics and the game still only happen at these frame boundaries, but inside there, just the collision is iterating. And so one reason that it's better, I think, to have your collision system be do sort of the checking perfectly inside it is because that means that the iteration happens at the smallest possible loop scale. So you're doing the least possible work per iteration, and then lofting everything else up to the sort of a larger time scale, which is good for performance, I feel like. Can't you have multiple views of the same file with Emacs? You can, but it's janky. You've probably already answered this in a previous stream, but I haven't been able to watch a lot of them. And as far as I know, the Q&A parts aren't put on YouTube. The Q&A parts are all on YouTube. They just happen right after the video. So if you jump 1 hour into any of the videos, the Q&A is there. What are you wearing on your hands? Oh, the bot will answer it. The bot will answer it for you, the hands question. For the Minkowski calculation, will we still be able to use the same procedure for a rotating hitbox or for diagonal space? For the rotating case, would we have to apply a transform to all the collision geometry to reflect a larger profile? So that's an excellent question. The answer is, it depends whether you're talking about animated rotation or static rotation. Okay? So essentially, Minkowski doesn't care if you're rotated. Minkowski's fine with rotation, right? So let's say I had a rotated rectangle and another rectangle that was rotated or something, right? The same sweep still works, right? The same sweep totally works in Minkowski terms, right? You still just get the exact right shape. The only difference is it's no longer a rectangle, right? So there you go. So it's like an octagon or whatever. So Minkowski still works. Minkowski works just fine with static rotation. Our cheesy implementation that we just did, where all we did was handle right rectangles anyway, obviously won't work. But GJK would work in this case just fine. What Minkowski cannot handle is animated rotation. So let's say that I've got a guy who's rotating over the time step. So he rotates from here to here, right? Minkowski can't handle that properly because that is, I mean, well, and to be fair, to be totally fair to Minkowski, Minkowski would still work. Like, real Minkowski would still work because you just envision this as a three-dimensional extrusion where time was along the other axis, right? So if you imagine what you were doing, here's time, here's 2D, I've got this thing, and I know I'm going from here to here where it's rotated, and I've generated this swept volume that kind of looks like that, right? And then Minkowski would say, oh yeah, just do the intersection test of that with whatever the other thing is that you were trying to intersect it with. And hey, it just works. And that's true. The problem and the reason that we can't do this is because it creates a concave shape. And it creates a concave shape that there's really no way to subdivide other than subdividing it like into time steps again. So Minkowski, the only place that Minkowski really can't help you in terms of the efficient implementations of it that we use that are based on concavity, that are based on convexity. The reason that things fall apart is just because of that convexity during that animated rotation. But that's only for animated rotation. So if you were willing to say that at a 60th of a second, I don't care about the small amount of rotation that's going to happen, and I'll just use either the beginning or ending rotation as my sweep, then it would work fine. But if you actually, for some reason, need to encapsulate that animated sweep in your collision section, it doesn't work anymore. And you have to have alternate strategies. I don't know of any one-step solution that works for rotating shapes. I feel like at that point, you're in a very difficult place. I would recommend never getting into a position where you had to handle that 100% animated like that, because that sounds really tough. I feel like you always want to try, if you can, to make it so that it's okay to just subdivide to a few discrete orientations that you care about and do the test against those. I feel like that's really the only probably sane way, unless someone knows an algorithm that's really awesome that I don't know about. How long have you been working on this current game? 50 hours is how long we have worked on the game so far. So a little over 1 week of programming time. But that's with explanations. So if you were actually to map it into my actual programming time, it'd probably be something like, I don't know, 20 hours, 10 hours, something like that. Is it possible to make assert so that it is possible to continue on assertion failure? Yes. We haven't done that yet, but obviously you can do that. That is not something we have done. We could do that in a future stream, but it hasn't been particularly important. Are you doing any cyclomatic complexity analysis? I have no idea what cyclomatic means. Cyclomatic. I don't think I've ever heard that. If you want to tell me what cyclomatic means, I could answer the question. How would you represent a large side-scrolling open world 2D where the character is basically just walking along the ground, so not really a platformer, but almost feels like a tile map would be a waste of vertical space between parallel paths, one high above another. Double linked list, triple for branching path nodes, I guess, comes to mind, but are apparently not good performance-wise. Any ideas? So I would just use, I would say hang on till we get to how we're actually going to represent the world fully at the end of this, because I suspect it'll basically be the same as you would use for a platformer, which is basically sparse placed things in the world is probably the best way to do it. Tile map is more what we're using for thinking about how we're generating the world, and I'm just not sure yet exactly what we're going to do, but I suspect we'll do something that's closer to what you would actually want for the platformer as well. Is it possible to, will you be considering trying to determine the point of collision? We are. We do. That's what we do. That's what we just did. So that's this. This is the code that determines the point of collision. And so we are accurately doing that now. That's exactly what's going on. Seems like the inability to robustly represent rotations in physics is why complex physics in modern games is so busted all the time. It might be, but there's other problems when you're doing a general physics engine. It's usually, honestly, rotation is usually not the worst of your problems. It's usually contact. Contact is usually where stuff gets really, really bad. But you're right that rotation is a big problem. It's just not the collision detection of it. It's the fact it's rotation's nonlinearity as it applies to contact that's the real bad news. Real bad news. So are we at the end of questions? I don't see any more questions. Oh, I meant determining the, okay, I see. Greenish, I meant determining the point of collision with the general GJK algorithm. Yes, we probably will do that. Again, I don't actually know if we'll do GJK. I just assume that GJK will be the most efficient thing for us to do, but we could also do hand-coded. So for example, the collision detector in Braid, I wrote the collision detector in Braid as well. And the way that it worked is it's a hand-coded rounded rectangle one. So the way that it works is it stores everything as the sum of a square and a circle, and it does all of the collisions by hand in hand-coded things that can do like raycasting versus this and overlap testing versus this and so on. So it's possible, and Braid is the only 2D game that I ever had any code in, I think, that I know of anyway. Collision detection wise, and so maybe we'd do something like that because it worked pretty well in that game, but I don't know, like we'll see. Are we doing a Raspberry Pi port just for the heck of it, or is there a deeper reasoning behind it? Yes, the reason that we're doing a Raspberry Pi port, or I don't know if we're going to do a Raspberry Pi port, but we're going to do a port to some platform where everything is spec'd and we can boot straight to the game with no operating system. And Raspberry Pi at the moment is just the best platform for that I could find. If there's like a more powerful piece of hardware 2 years from now when we're done with the game and it comes time to do a Raspberry Pi version, then we'll do that version instead. But right now, as far as I know, the Raspberry Pi is the only thing that does that. And so I will be looking for other options in Raspberry Pi. The Raspberry Pi is not necessarily something that I have any specific affinity for, other than just it's completely documented and you can boot straight into the OS, straight into your game with no OS, and that's what I wanted. Cyclomatic complexity, a direct measure of the number of linearly independent paths through the code. No. And we never will do that analysis either. So it looks like we are at the end of the questions. End of questions. So I think that's about it. BeagleBone Black better than Raspberry Pi, I think someone was saying. Yes, but BeagleBones aren't documented. Am I wrong about that? Let's find out. Right? Which 3D graphics accelerator is it in the BeagleBone Black? Like basically, if they do not have the full documentation from the hardware manufacturer of the 3D graphics accelerator, then it's not useful to us, right? And so I don't know if they do or not. So you'd have to look up, is the 3D graphics accelerator fully documented on the BeagleBone Black? And I mean fully, as in no driver required. We can write directly to the hardware and have full access to all its capabilities, because you can do that on the Pi. So if you can do that on the BeagleBone Black, we might consider it, but otherwise not. Ryan reads, can't you do that on a PC? Write yourself a boot sector, put it on a USB stick, and boot straight into your game with no OS. No, you can't. And the reason that you can't is because the graphics cards aren't documented. So you can't actually use them. You can sort of use them. You can half use them and try to go from the reverse engineered stuff and kind of maybe use them. But I want a machine that's entirely documented so that we will be able to use the entire machine. And not have to tiptoe around NVIDIA's NDA or something. Well, not NDA, trade secrets that they won't even tell us how to program, you know, the card or whatever, right? Because that's just lame. All right, so I think that's it for today. I am going to say that we have finished our stream. Thank you very much for joining me here for breakfast time, Handmade Hero. I'm glad our collision detector is now working smoothly. I like the feel of this as well. I like how it works. I feel like how we want the player to move might change a little bit, because next week what I'd like to do next week is get animation going for the guy, so that he hops, you know, along as he moves. And as we play with that, we're gonna have to see how we want it to feel in terms of how it goes. And when I say we, I really mean me, because all of the movement's gonna be tuned so that I like it. And I know there's a bunch of different people have different preferences of how movement systems work. So I can't really promise that it'll be the way other people might want it to feel, but it'll be the way I want it to feel. And of course, one of the nice things about Handmade Hero is all the source code's available. If the game ships and you don't like the movement, well, that is a perfect reason to study up on the series, learn how to fix it, and go in and change it to how you want it to work, right? So that's pretty cool. Anyway, thank you very much for joining me for this episode of Handmade Hero. It was a pleasure coding with you as always. And if you would like to follow along at home with the source code, you can pre-order the game on handmadehero.org, and it comes with all the source code. You can download it every night from a link that you'll get in your email. And it also comes with the debug assets that we've been using, you know, the little guy and the backdrop and that sort of thing. So you can go ahead and pre-order that if you want access to all that stuff. If you want to just support the video series, there's a Patreon that you could subscribe to. And if you're trying to follow along at home and learn from the series, there's a news and forum site that I highly recommend checking it out. It's got the schedule for the week every week, so you can go look. For example, I'll post the schedule for next week, next Monday, so you can see when all the times will be. There's an episode guide that allows you to catch up with past episodes, and it's got good time markers and stuff that people contribute. There's a coding resources page that has ports to Linux and Mac if you're trying to follow along on a different platform. And finally, there's a discussion board that you can go to that allows you to ask questions and talk about the series with other people. And it's also a place where people help me out. If they spot typos in the code, they'll post them here. And that's helped tremendously to have other people watching, because when I'm talking on the stream, I can't always concentrate on the code that well. And really, it helps. So thank you, everyone who writes in and says, hey, you forgot to do blah. That's really helpful to me, and it helps make sure that we don't spend a ton of time on the stream tracking down typos. So that's it for today. I will be back Monday, probably 8 p.m. PST on Monday. So I hope to see you all there. Have an excellent weekend if I don't see you guys somewhere online. Thanks, everyone.